Hello, welcome back to Calculus Corner, a series where I go over your math problems here on my channel. Post yours in the comment and maybe I'll get to it next time. Here we have, given f of x is a continuous and differentiable function on the interval -3 to +6, create a graph with critical values at x equals -1, 2, and 4, inflection points at x equals 0 and 3. We find that f prime of x is greater than 0 on the interval 2 to 4, and that f of 0 is the same as f of 6, which is 5. And our direction is to create a graph. Now this problem may look intimidating, but we need to take it one step at a time. What are the bounds it gives us? And we have to make a graph. So let's make a graph with these bounds. So when we make our graph, what really matters is right here we have the bounds, -3 to 6. This is the portion of the graph we care about, so that's all we need for the x values. In terms of the y values, all we know is that at one point it hits, or actually 2 points, it hits y equals 5. So I wanted to make sure all that was included. The first thing we're going to do is we're going to take a look at this first point they give us. The critical values are at x equals -1, 2, and 4. How do we show that on a graph? Now, the critical values are at x equals -1, x equals 2, and x equals 4. And to remind myself of that, I'm just going to make some dotted lines throughout this graph. Now, why am I making dotted lines instead of points? Well, we don't know where the points are along this line. We just know there's some sort of critical value along this line. We don't know at which y value that happens, so this is the best we can do for now. Then our next point, inflection points at x equals 0 and x equals 3. This is a different derivative graph than critical values. Critical values are made using the f prime function, while inflection points use f double prime of x. So this is an important piece of information, but it doesn't help us much with critical values. So what else could help us? Well, f prime of x is greater than 0 on the interval 2 to 4. What can that tell us? Let's take a look at the graph. So because of this tidbit of information, we know that the graph is going to be increasing between these two critical points. So to remind myself of that, I'm going to put a plus there. Now, what about the rest of the graph? Well, by definition of critical points, once it hits a critical point, the slope will always change, either from positive to negative or negative to positive. So from 4 to 6, we know it's going to be a negative slope because of that definition. Same with from -1 to +2. We know it's going to be a negative slope. And then finally, out here on the left, we're going to have a positive. Finally, this last tidbit of information, f of 0 equals f of 6, which equals 5. This is telling us our only guaranteed points on the graph, and it's that f of 0 is at 5 and f of 6 is at 5. Now, this tidbit of information is probably the most concrete we have. It's just telling us where a certain point lies, and it's telling us that f of 0 equals f of 6, which equals 5, which means that at the x value of 0 and the x value of 6, our y value is 5. So I'm going to draw those points on here. The inflection points are going to be what tell us when the graph turns from a downward facing concavity to a forward facing concavity, and I'll show you on the graph. Now finally, for the hardest part of this problem, what do the inflection points tell us? Well, we know that they're going to happen somewhere along x equals 0 and along x equals 3. So I'm going to draw another line, sort of like the last one, but I'm using longer dashes to try and show that they're different, right? And I'll just try and remember that that is at the origin, because it's kind of hard to see. What this tells us is it tells us when our graph will change from a downward facing slope to an upward facing slope, right? And these two lines actually have 4 different sections of it. We're either looking like one of these two lines or looking like one of these two lines. This would be defined as concave down, and this would be defined as concave up, just based off of how it looks like their smiles are. Are they frowning? Concave down. Are they smiling? Concave up. So we know that over here on the left, we must be increasing. So I'm going to begin to draw this. Once I hit this dotted line, we know that we must be decreasing, right? But we are still using the concave down slope. Notice how this all looks like one elongated frowny face. But once we hit this dot, we have to change to one of these two lines. Now, am I going to start going up? No, because we are still decreasing. So I'm going to erase that. What happens is we need to change to the other concave up line, which will be continuing to decrease. So it will look more like this, right? That looks more like this line for the concave up than anything. But we hit the dotted line once again, and we change to a positive slope, right? But wait, we once again hit a point of inflection. Now we're still increasing, we're just going to use the concave down slope instead. So we're going to curve it back out, right? Now we're hitting a negative slope once again, but we are still in a concave down inflection point. Now, I didn't really give myself enough room here, so I'm just going to erase that, go a little bit higher, and bring it back down. And that would be our graph. Now, the y values may not be exact, but they're around what's the right answer, and that's what matters here. Thank you for tuning in to my second edition of Calculus Corner. If you have a problem you want me to solve, leave it down in the comments below and maybe I can get to it. Like and subscribe, and I'll see you next time. Thank you.